Consider the above layout of room and pillar coal mines, one with square and the other with rectangles. So you have to consider those images I showed you, one being square and the other being rectangle. So the area supported by the pillar covers the area above it and the area midway to the middle between the adjacent pillars, neighboring area tributary to it. So thus, in a typical room and pillar layout, the average stress on the pillar for square pillars is, so we said the pressure there. So now we know this, right? This is the stress that is being carried from the top. We already know this. The H is representing the distance from where the pillar is to the surface or to your reference point. That is the H. The G is representing your gravity, and this man here is your density of the material. And so I can also rewrite this here with the gamma, which is the unit weight of the material. And I have weight of the ore, which is the space between the adjacent pillars. And this being the width of the pillar to the power 2 divided by width of the pillar. So this component here times the pressure it is carrying is equal to P, which is the total load on the pillar. This is pillar. The total load on the pillar over the area of the pillar. And that is what we call, so if I want to calculate a typical room and pillar, the average stress. So if I ask you to calculate the average stress of the pillar, this is the formula you are going to use. So, or the average stress, you can now use this, which is this symbol. Sigma is equal to 1 plus this component. And this one is the vertical stress that we computed initially when we drew this diagram. And we wrote here as Z. So this thing we expressed here is the vertical stress, and that is here. And then the whole of this is representing the components of the pillar itself we are bringing on board. And that is what we call the average stress of the pillar. So any unit weight of rock or coal underground is supporting a vertical load equal to the gravity weight of the column of rock extending all the way to the surface, which is why the vertical component is there. Depending on the rock type, it usually ranges from, so here it is saying that the unit weight, okay, the unit weight of the material, which is the this symbol, can range from 1 pound per square inch to 1.2 pounds per square inch, which when we bring it to our usual metric system that we know, it is from 6.895 to 8.274 kilopascal or kilonewton per square times your H, whichever distance it is from that point to the surface. Then now when you are done, you don't forget to bring your horizontal, the deformation in the x-axis, which is the horizontal deformation. You bring that one, and that one makes use of your Poisson ratio. Therefore, in estimating the in situ stresses for a point located at some depth below the surface, to obtain a vertical stress, you simply multiply the depth by whatever value you are going to obtain for the unit weight. then your H can be estimated from the equation, which is up here. So let's solve this example. It says that you should determine the biaxial. The biaxial here should not cause any confusion. Biaxial simply means that there is that system which says, if I subject anybody to a stress in a particular direction, it provides a corresponding stress in the other direction. So it is by 2. So we are asking for the vertical and horizontal. Instead of saying that, we say biaxial stresses. So determine the biaxial in-situ stresses in the undisturbed virgin coal in a coal mine, which is at a depth of 900 feet. So I am to go and start a coal mining. No work has been done there, but I want to have a fair idea the pre-stresses that exist at 900 feet if I am to go and start work. So at that 900 feet, we have said that the unit weight of material usually ranges from 1 to 1.2. And we have been given the Poisson ratio of the substance. So we can calculate our vertical stress. So the vertical stress is always, let's say it's like this. Vertical stress is equal to gamma times H, or density G H, isn't it? And this man here is the same as that. But they didn't give us the value, the exact value for the unit weight of the material. So we are going to work using estimation. And since the theory is telling us that unit weight lies from 1 psi to that of 1.2 psi, we are going to do it for the minimum value, which is 1, and do for the maximum value 1.2. Then we have the range. So you only pick your formula. Sigma V is equal to gamma H, and you first substitute the value of 1 here, and you have your 900 feet. And there is the answer. Then again, you come again and pick your sigma V is equal to 1.2 times your height, which is 900 feet. And there you have it. You have your answer again, which is 1,080 pounds per square inch. You are done. You have been able to get a fair idea. You have not started mining, but you've been able to predict what pressures you expect to exist when you go to a depth of 900 feet to go and work. And this is what we term as the pre-mining stresses. Then, whilst you are there, you should expect a corresponding forces on your x-axis acting on the pillars or the walls. And so you use this formula, and that is also your Poisson ratio over 1 minus the Poisson ratio times the vertical stress. So here you have, let me clean this. So here too, again, you have sigma H is equal to this formula, V on 1 minus V, sigma V. So remember, this is your Poisson ratio. It was given as this. And because we were not given the unit weight, we had to calculate for maximum and minimum values to get this and that. So again, if we want to calculate for the horizontal stresses, we will pick the first sigma V we calculated, which was 900. Come and substitute it here. Use the Poisson values. So we have sigma H is equal to 0.2 on 1 minus 0.2 times the 900 feet, which is corresponding to the gamma of 1. 900 pounds square inch. And what will be the value? This is it. So you have sigma H is equal to 225. So if you have calculator, you can punch and see if the values I've written there are correct. Then we have your second one. Again, you pick sigma H is equal to 0.2 over 1 minus 0.2. Multiply that by this value, which is 1080. Again, after you have done that, you come up with 270 as your answer, PSI. So it means that assuming you start work and you bring your material to the lab, then we test and tell you and we tell you that your unit weight or the density of the material is 1. It means you are going to have a pre-mining stress in terms of the vertical to be 900 psi, and that of the corresponding horizontal to be 225. Okay, so now let's make things simple. Everyone, wherever you are, if you have a sheet, try to work this out. Assuming we have done the test and we realize that the value for the stress is 1.08. 1.08. What will be the answer we are going to have for vertical and horizontal stress? Let's work it out. So we have gamma to be equal to 1.08. So let's work it out. So using that value, you work for this and work for that. So let's give ourselves some few minutes to work it out. So this is what we are solving. Try it, so you might not have time to try it again. Okay, so I also got the same answer, so we are good to go. So your final answer is presented this way because we have a range. That is why you have this. But in our case, we had sigma V of 900 to be equal to 972 psi and not in a range. Then our sigma H 900 to be equal to 243 psi. That is what we are getting because ours is not in a range.